workshops we have. So I just want to check something online. Yep. Okay, I'm happy because I was just making sure that actually we were going live, because I realized I hadn't clicked the go live button, so my apologies for that. So let me go forward a little bit more now. And one of the questions that came in this week was really about, can you explain the application of curve fitting, sort of Tafel to Butler Volmer equation from linear sweep voltammetry. So I will dig into that, I will say, in a minute. And I will also dig into detecting heavy metals. I will definitely dive in and discuss detecting heavy metals. I'll also discuss fabricating an immunosensor on a carbon electrode. And I'll also have a little title here, Rethink It to Shrink It, and I'll discuss what I mean by that. I'll say very quickly that in microfluidics, there's this term lab on a chip. And I think there's a problem with the term lab on a chip because it suggests that you take laboratory procedures and you just apply them straight away into microfluidics. And I think, no, you have to be a bit more, how can I say it, sophisticated than that. So we will discuss microfluidics and in vitro diagnostics, IVDs. And I'll also discuss cortisol sensors as well. So first of all, I'm going to discuss Tafel plots. I know this is really getting into, I wouldn't say deep electrochemistry, but we are getting into more kind of fundamental electrochemistry here. But first of all, when I was doing my PhD, it was quite a while ago, I had a colleague in the lab who was doing corrosion studies. So I'll describe what he did doing his corrosion studies. The first thing that he had what's called a rotating disc electrode. Personally, I've owned rotating disc electrodes. I did my PhD on rotating disc electrodes, so I think I fairly well understand rotating disc electrodes. If you're a biosensor developer, it's my personal opinion, but I'm not a great fan of rotating disc electrodes for biosensor developers, because you'll never the regime of rotating an electrode like this is never going to be something that you can. Well, never. You wouldn't reduce it down to what's called an IVD platform, an in vitro diagnostic platform. But anyway, he was using a rotating disc electrode, which rotates and makes sure there's a constant fresh supply of material to the electrode. Now, the reason that was happening is because he wants to do, in the end, a Tafel plot. And the Tafel plot assumes that the current limiting phenomena is just electron transfer between a redox molecule and the electrode. And therefore he was rotating, and in fact he was rotating at 1600 RPM, 1600 revolutions per, it says here per minute, which is wrong. I should have been just, it's 1600 RPM, 1600 revolutions per minute. The second bit is wrong. But he was rotating very fastly because essentially what he was trying to do is just make sure that there was lots and lots of material getting to his electrode. So he rotated really fast and made sure that he was under what we call electron transfer control. This was his data as well. So you can see here that he's what he's done is he's swept, or he's changed the voltage in a sort of linear sweep voltammetry fashion from minus 1100 to minus 600 millivolts. All the time he's been rotating at 1600 revolutions per minute, and he's recorded the current. Now he's displaying the current here as current density. So he's divided the current by the area of his electrode. In this kind of work, I think we were typically using, I think it was an electrode with a diameter of about, I want to say about 5 millimeters diameter. So here he is, he's rotating the electrode. He's sweeping, and he's sweeping really slowly. Now, the reason he's sweeping really slowly, like 5 millivolts per second, is he doesn't want what's called charging current. He doesn't want, every time you change a voltage, you can get something called a charging current. So he's rotating really fast so that he's only under electron transfer and he's not under any diffusion control or mass transport control. And he's sweeping really slowly on that voltage because he doesn't want any charging current. So he wants his signal to be essentially as pure as possible. That's only the signal's only from electron transfer limitations. Now all he's done here then is just plotted it. He's logged the data. The first thing is you can't log negative numbers, so you have to turn these negative numbers into positive numbers. It's, just times it by -1. It's not so hard. And then he's logged everything. So this part of the curve here became this part of the curve here, and this part of the curve here became this part of the curve here. Now what happens is, I know that many people watching our channel, many people watch us just have a strong maths background, so that if you're doing a log of the current, you can't log 0. It's indeterminate. So this starts going to infinity quite quickly. So you can't quite log where it crosses the boundary here. So that's why it's like, it's changing, and it rapidly gets really. And now that's the point at which you're sort of, you have a maths issue. You can't log 0. But what software does, or what you can manually do, I think my colleague who was doing this quite manually, was you get, they call this the Tafel plot essentially. He was doing corrosion, so he was particularly interested in what's called the corrosion potential. So where these two lines sort of intercept approximately at this point here, he could draw a line down, and that would tell him, oh, that's my corrosion potential. Now he would draw in an imaginary line here and an imaginary line here, because what he's doing is he's drawing in the linear region before he starts running into this sort of curved off region here. Now these are kind of Tafel slopes, and from there then he could determine. So this is, first of all I should say, this is he called it his corrosion potential. He called this his kind of corrosion current. The higher your corrosion current, the higher your rate of corrosion. And then he was able to calculate his alpha. Alpha is a sort of way of knowing the symmetry of this redox process. I would say that this was asymmetric, that actually the oxidation is happening at a much faster rate than the reduction. You can see it in the curves here, that when you go past here and you start going to this anodic process or oxidation process, you could even call it a corrosion process, it increases quite fast, whereas in this region, it's all sort of the slope, it's just gently rising, but then you hit a sort of moment here when you cross here and start doing oxidation, it goes off quite quickly. So from that slope, he's actually able to tell alpha. I don't know what alpha is here, but I would, if it was symmetric, if both slopes were the same, then alpha would be essentially 0.5. But when that slope is greater than that slope, then that suggests that alpha is greater than 0.5 on this side. And actually, I got that the wrong way around. Actually, I realized that. In fact, I should have to flip these in order to do that. But this says that this is, how would I put it, is asymmetric. So I might cover this again in another week, because it is it's, as I say, it's getting into fundamental electrochemistry, what we're describing here. But in order to get a Tafel plot, you do have to actually really control the conditions. Rotate very fast, or control mass transport, and scan very slowly. And then it's simply, get that linear sweep, log it. Once you've logged it, you kind of you sort of draw in these imaginary lines, and these are your Tafel slopes, and from your Tafel slopes then you can calculate your alpha values, because F is Faraday's constant, R is Rydberg's constant, T is temperature. So F is like 96485 coulombs per mole, I think. R is Rydberg's constant, which is about 8.314, and T is temperature. At room temperature, that'd be at like 298 Kelvin. So the rest of it's known to you. I'm going to go a little bit faster now. So question number 2 was really around somebody was wanting to know about how to measure lead, how to measure heavy metals. We do have something called the spectrum sensor, which I've put a link here. And we have reported on this kind of work in the past, where we are able to take samples, put them onto our sensors, drive them on, we call it our Sensi All platform, and we're able to measure the concentrations of things like lead and copper. So we have sort of demonstrated that we are able to do lead in the sort of 1 ppb to the 200 ppb regions, and and we've obviously displayed our data in the past, so we are very familiar, can I say, with recording heavy metals. Now, if every time you see a link in this webinar this morning, by the way, the link will also be underneath the videos as well. We're also able to do copper. We have discussed it in the past. Here we're looking at 200 ppm of copper up to 1471 ppm of copper. So heavy metal systems can be detected by ZP technology. Question number 3 is building an immunosensor on a carbon electrode. So first of all, they are using our hypervalue carbon screen printed electrodes. I do have a link in a minute. Now, I suggest if people are using our hypervalue carbon electrodes, I will link to this page in a minute. Choose the sheet of 300 and choose the perforated cut. The perforated cut means that you get them in a sheet, but you can just pop each electrode out, because we've essentially perforated around the electrodes little holes, so you can just pop them out and use them. It's just the most economic way of us manufacturing them, and the most economic way of you receiving them, and then you can just release them from the sheet and use them as you see fit. So I have put a link to that as well, so if you see a link pop up, then you will find it. Now they're they're going to build an immunosensor or a receptor sensor on a carbon electrode. They've received the hypervalue carbon electrodes, and they have cleaned them with deionized water. They say aqua demineralization, so I understand that's DI water. I've added in the term boron carbon oxynitride. I had to kind of look that up, but they're adding a drop of BCNO. So this is, I've heard of boron doped diamonds, so I can understand where this kind of material is coming from. And I can see from the data that what it does is it essentially increases the surface area, but I'll discuss that in a minute. So they put a drop on of that, and they leave it to dry for 1 hour, and you can see the effects of it in their data, and we will discuss that. Then they put the drop of this SARS-CoV-2 receptor onto it. Now, what I think is interesting about this is it's not clear to me how they are coupling this macro molecule to that carbon electrode. I can understand that maybe in the literature it just says it just sticks, but have we done this? It's not clear to me that there's a strong covalent bond between this BCNO and this SARS-CoV-2 RBD receptor. So I'm a bit concerned about that, let's say. Now, as they do each process, they do a differential pulse voltammetry. So ZP does have, we definitely have, we definitely have videos about voltammetry and differential pulse voltammetry. But differential pulse voltammetry is a good technique when you're doing electroanalytical techniques. So I have, essentially no issues with what they're doing, but I will discuss their data now. So what's happening here is they start off with, they've washed the electrode. That's pretty good idea. They've washed it, and they've tested it with essentially ferricyanide. So they do a sort of a differential pulse voltammetry sweep along here, and they get a peak for ferricyanide. Then they do the functionalization with the BCNO, this boron carbon oxynitride. It increases the surface area, and the DPV peak goes up. So that's within their expectations. So this red peak here. Now, what is not in their expectations is that they put this receptor down on top of the carbon, and that should essentially block the surface, and actually the signal should drop down, but it doesn't. Now, why is this? So I think it's either two things. Either actually you're trying to put the receptor down, but it's not really sticking to the surface, so all you're ending up doing is actually you're doing an extra wash on the surface. So you think that you're doing this deposition. Now, I do notice that, in fact, when I look at your guidelines here, you do actually you do drop it on the surface, which is interesting to see, because it would suggest that that would just dry onto the surface and sort of stick to it. You may have an extra rinse step afterwards that you don't report here, but you don't report a rinse step, so I can only assume then that actually it's just dropped and dried. So I do agree with you that if that receptor is truly sticking on top of that surface of BCNO, the signal should drop. But in fact, it's not. Now, either because now, so your increase in signal is either due to you've essentially washed the surface by doing that deposition, but in fact the material didn't stick to the carbon electrode, or, this is a bit more unusual, that the ferricyanide, which is negatively charged, is actually, it's your receptor for some reason is, I mean, this is a bit speculative for me. There's some sort of positive charge on your there's some sort of negative charge on your electrode. By putting this receptor down, you've decreased that negative charge. So the ferricyanide actually was a little bit electrostatically repelled from the surface. But when you put the protein down, you blocked it, but you had a bigger effect on an electrostatic repulsion. And in fact, now the ferricyanide, which is negatively charged, is able to make to the surface easier. Now, that's an electrostatic explanation as to why your signal went up when you were actually expected it to go down. If you want to prove that out a little bit, you can try, rather than using ferricyanide, ruthenium hexamine, because ruthenium hexamine is positively charged. So if you ever want to understand, do I have electrostatic interactions that I didn't know I had, you can change the charge of your mediator by going from ferricyanide, which is negatively charged, to ruthenium hexamine, which is positively charged, and you can try things like ferrocene, which are neutral. I'll give you an example of where we've seen some unusual behavior in the past as well. So this is the sort of bare electrode that's washed. This is the electrode that's had the surface increase with this BCNO. And this is the signal after you've added the receptor. And as I agree with you, it's actually unusual that that would be the case. This is some work that we've done in the past. What we did was we took the carbon electrode and we put this pyrene NHS down on it. So I can't see in your procedure that you do have a way of covalently bonding to that, to your receptor. So I am suspicious about that, because what we do then is we put down this reagent. These NHSs are quite quite reactive. Then we can put down, in this case, an antibody. Then we block the surface to stop non-specific binding. This is something actually you should try. Every time we do a functionalization, we do a cyclovoltammogram. So we start off with a sort of pristine electrode, and every time we functionalize, the CV gets more and more distorted. I know you're doing differential pulse voltammetry, but let me suggest that you follow your procedure, but actually you follow it with cyclovoltammetry. I would be interested if you did exactly what you've been doing today, but rather than doing differential pulse voltammetry as you're doing it as a quality control to make sure that you are processing the surface, actually do it with CV and send me that data. It'll be interesting just to compare and contrast. You might find that differential pulse voltammetry for some reason is actually stopping you immobilized, but I don't believe it. But I'd like to see a CV, the same procedure, but followed using cyclovoltammetry, which is what we've done, rather than differential pulse voltammetry. Now, when we were testing this sensor, we have a surface of antibodies, and we were using ferricyanide as well. So you can see that what you're doing is fairly similar to things that we've done at ZP as well. But what was unusual was that when we, let's say, tested in the absence of any antigen, we got a differential pulse signal, and the magnitude of that signal increased with the more and more binding, which is similar to what you're doing, because we're binding to the surface, we're therefore blocking the surface, we would therefore expect the signal to go down. But in fact, the signal is going up. And in this paper, we did argue that there was obviously some sort of negative charge associated with our surface, but when we bound to it, we actually reduced the negative charge, and the ferricyanide was therefore able to access, or the negative redox molecule was able to access the surface easier. Now, I don't think we really proved that. We could have proven it by, as I say, trying things like ruthenium hexamine and seeing if the situation changed, but we didn't prove it, we just stated it. So it was we left it as a theory. But we have also seen this unusual behavior. So my suggestions are, I'm not convinced that your receptor is actually bound to that surface of, I think, BCNO. But do the procedure again, but follow it by cyclovoltammetry. And also read this paper, because you can see that we've also seen these kind of unusual phenomena ourselves as well. I'm just hoping that what I'm going to do now is go forward a little bit. Now, I say here, rethink it to shrink it. So I'm going to go into a sort of essentially a new question. But this is something that happens quite a bit, that we will get an inquiry which says, I have this new assay. I'm just going to move my image out of the way. If you see a link, by the way, I will have already put the link underneath the video. But what I'm saying here is, we do get inquiries that say, I want to make an assay, and this is my microfluidic device. Now, what you find sometimes is these microfluidic devices are extremely complicated. For example, they could have something like 22 steps involved in them. Now, what's happening is people are taking lab procedures and exactly translating it into a microfluidic device. But if you're going to do the shrinkage of assays and lab assays, you have to really think the workflow. You can't just translate what you did in the lab onto a device. You'll end up with a very complicated device. So in this case, the device was quite complicated, when really it didn't have to be. If we were trying to do a lamp assay, we would do it with no pumps, no liquid reagents. At ZP, we would actually just take one of our products. We'd have a sample chamber on top of the electrode. We would do what's called the lysis and amplification in that chamber. And then we would actually do the signal read in real time in that chamber as well. So it's really, at most, a kind of three-step process. But when people come to us, they come with these very complicated devices and say, this is what I need. I think what they need to do is actually maybe have a consultancy with somebody like ZP to actually shrink down the complexity of what they're really trying to do. So we're able to make things like lamp assays actually, and we can do them in, we can do real-time measurements, and we can get these assays to work in something like less than 20 minutes. And these are sort of standard products on our website, and it's much simpler than people coming to us with just a cartridge design, which is very complicated, never going to be manufacturable in high volume and at low cost. Question number 5, we do get a lot of inquiries around our cortisol sensor, and we're delighted that people are obviously interested, can I say, in the cortisol sensor. What we say to people is, if you want to access the cortisol sensor, if you want to procure it, you can really only do this through two ways: either procuring an engineering contract with ZP, and I'll put a link to that underneath the video, or we're also making it available to people who have actually purchased our new EMA potentiostat. So hopefully I will have a link to that as well. So we either will do it with people who have bought the potentiostat, or we will do it with people who are actually running a project with us. I also want to say, if you're in India, we do have an India distributor who you can reach out to and get support. So with linear sweep voltammetry, getting a Tafel plot from linear sweep voltammetry, the first thing you need to do is actually get the setup right, which is probably control the mass transport using something like a rotating disc electrode, use a very slow scan rate. You'll get current versus potential. You have to log that current. First of all, the current has to be shown as current density. So divide your currents by the area of electrode. Then you have to log it. You can't log negative currents, so you have to pretend that they're positive currents. You'll get to the Tafel curve from that. From the Tafel curve, you can, if it's corrosion, you can estimate your corrosion potential and your corrosion current. And from the slopes, you can calculate alpha. And alpha is a kind of symmetry value. It tells you whether you're more prone to oxidation or reduction. So in terms of heavy metals, ZP has plenty of data on our website that our technology will detect heavy metals. Fabricating on a carbon electrode, I do understand that the anomaly that when you put the receptor on the surface, which should be blocking the surface, your signal goes up, which suggests that either your surface you haven't blocked your surface, you've actually just washed it by trying to do that, by trying to add that receptor, I'm not sure that I can see any evidence that actually that receptor is got any way of binding to that surface in a specific manner. I think I don't think there's much evidence for that. We would have used a coupling agent. Maybe you are using a coupling agent. And then the last reason could be that ferricyanide is negatively charged. For some reason, that surface is acting quite negatively charged as well, and there's a repulsion. But when you actually put that receptor on there, you decrease that negative charge, and actually now it's easier for the ferricyanide to get to the surface. Question number 4, if you're doing things like lamp assays and your cartridge is complicated with pumps and valves, it really doesn't have to be that way, but you do have to kind of talk to somebody probably at ZP. And with a cortisol sensor, we make it available either through projects. We have so many inquiries around it. We're very selective in how we release this cortisol sensor. So either through a project, or we will put some sensors with our EMA potentiostat as well. So if you've got any questions of ZP, I realize it's 2 minutes, it's 28 minutes so far, just reach out to us and we'll be happy to answer them. Okay, thanks very much.